In this video we discuss the column generation method for the cut-in stock problem. Let's start by introducing the cut-in stock problem. In this problem we are given stock rolls of width W, and we need to determine how to cut these stock rolls so that we produce BI units of width WI for I between 1 and M, while minimizing the total number of stock rolls that we are using. As an example, consider the situation when we have 15-foot boards which we need to cut into smaller pieces, and we have the following requirements. So we need 84-foot boards, 56-foot boards, and 107-foot boards. So in this case, W capital is equal to 15, so this is the width of the long boards, and there are three different types of shorter boards that we need to produce. So M is equal to 3, and WIs are given by 4, 6, and 7. So W1 is 4, W2 is 6, W3 is 7, and BIs are given by 80, 50, and 100 respectively. So there are many different patterns according to which we can cut the board, and we refer to this as the cut patterns. Or sometimes you also call this the knife settings. Let's consider some examples of the cut patterns. Assume that this represents our 15-foot board, and we can cut it as follows. Let's say we need 4-foot boards. We could cut it into 3 4-foot boards. And there will be some waste of 3 feet remaining. So this will be waste. So, and each of these pieces is 4 feet. Alternatively, we could cut the same board according to some other pattern. Say I could cut one board of 4 feet. Then we could have a 6-foot board, and we still have 5 feet remaining, right? We could cut another board of 4 feet. So this is a 4-foot piece. And here we have the waste of 1 foot. Now we could represent the different cut patterns by a 3-dimensional vector. So because we have 3 different type of smaller boards that we need to produce, we could represent this by a vector A given by the following components. The first component will be denoted by A4. So this is the number of 4-foot pieces that we are going to produce in our cut pattern. Then we will have A6 will be the number of 6-foot pieces, and the number of 7-foot pieces will be denoted by A7. And this vector will represent our cutting pattern. For example, in this case right here, we have 3 4-foot boards, and we don't have any 6-foot or 7-foot boards. So our cut pattern can be represented by the vector 3, 0, 0 in this case. Now for this example, our cut pattern is given by the vector A, which is A4 is equal to 2. So we have 2 4-foot pieces. Then we have 1 6-foot piece, and we have no 7-foot pieces. Now, to solve our problem, we could try to enumerate all the possible cut patterns, and then all we need to do is to decide how many boards we are going to cut according to all these different cut patterns. Actually, to avoid the ambiguity, let me use capital A to represent these cut patterns. So we have A, and in fact we are going to use some index J also to enumerate these patterns. So let's say this could be our first pattern denoted by A1, and this could be some other pattern that will be enumerated according to some index j, so it's not necessarily going to be the second pattern that we consider, so I'm just going to put some arbitrary index j here. And next we are going to actually consider all the different cut patterns that we can have for this particular example. This table represents all the non-dominated cut patterns for our problem. For example, our A1 is given by this column right here. Remember, we had 3 4-foot boards and then no 6-foot or 7-foot boards. Then our column AJ from the previous slide was given by 2 1 0, so this is actually our A5. And there are 4 other patterns that are non-dominated. It means that all other possible feasible patterns are inferior to the patterns that we have here. For example, 1 0 0 would be a feasible pattern, meaning that we just cut 1 4-foot piece and then the remaining 11 feet will be a waste, but clearly that pattern is dominated by the first pattern right here. And this can be said about all other possible patterns. For a pattern to be feasible, we need to make sure that 4 times A4 plus 6 times A6 plus 7 times A7 is no more than 15, right? So because if we have A4 pieces of length 4, A6 pieces of length 6, and then A7 pieces of length 7, the total length of the pieces that we cut will be given by the left-hand side of this inequality, and that cannot exceed 15. So, as we said, our problem now reduces to determining the quantities of boards that we cut according to these different patterns, and we want to minimize this quantity, right? So let's denote by xj the number of boards cut according to the pattern J. Then our objective is to minimize the sum of xj's, so we have minimize x1 plus x2 plus x3 plus x4 plus x5 plus x6 subject to, and then we have the pattern A1 multiplied by x1, so we have 3 0 0 times x1. So, you know, the first entry here is gonna give us the number of pieces of length 4, then the second entry will give the number of pieces of length 6, and then the last one the number of pieces of length 7. And because we cut x1 boards according to this pattern, this will be the total quantities of the corresponding types of pieces, right? So then for the second pattern we have 0 2 0 multiplied by x2. Then for the third one it's 0 0 2 multiplied by x3. Then for the fourth one 2 0 1 multiplied by x4. Then we have 2 1 0 times x5. And finally the last pattern is given by 0 1 1, and we multiply this by x6. Let me move this to get some more space. And now the quantities of each type of boards that we need are given on the previous slide. So they're 80, 50 and 100. So we need to have at least this many pieces of each type. And of course we require all the variables to be integer. So x1 through x6 are non-negative and integer. To make the problem simpler, we are going to drop the integrality constraints and we will focus on the LP relaxation of this problem. And relaxing integrality constraints is very reasonable from a practical perspective, because typically we would solve such a model when we deal with large quantities of boards, and then we can easily obtain a good approximate solution from this LP relaxation to our integer program by just rounding up the optimal values of all the xj's. So assume that you have the optimal solution to the LP relaxation with the objective value given by zLP star. Then by rounding up all the xj's that are fractional, so we'll have no more than m positive xj's, right? Therefore, the objective will increase by no more than m, and the value of this rounded integer solution that we'll denote by zip will be given by at most zLP star plus m. And of course, the optimal value for the LP relaxation will be less than or equal to the optimal value for the integer program, which will denote by zip star. So this will be less than or equal to zip star and then plus m, right? So the value of the integer solution we obtain by solving the LP relaxation and then rounding up all x's will not exceed the optimal value of our IP plus m. And typically m is very small, so we obtain a very good approximation for our integer program by solving the LP relaxation. Also, let's assume for simplicity that we have the equality constraint here instead of the inequality, just so that we don't have to deal with the excess variables. So from a practical perspective, this means that we are essentially targeting to satisfy the demand exactly, and we don't want to have any excess. So now we can solve this LP, right? But looking at the way we formulated it, we can have quite a few patterns actually when we consider the practical scale problems. In our example here, m is equal to 3, right? But in general, m could be higher, and also our W capital, the width of the boards that we consider, can be larger, and as a result you can have a lot of different cut patterns. In fact, there can be too many for us to be able to handle this in a single tableau. So essentially the issue with this LP is that the number of columns that we have here can be huge, and we don't want to really express the whole LP explicitly. Instead, we want to find a way of determining which cut patterns we need to restrict our attention to, so that we don't miss the optimal solution, and at the same time we don't need to deal with too many columns in our LP. And this leads us to the column generation approach for solving the linear programs. In the column generation approach, we don't really formulate this LP explicitly because there are too many columns. Instead, we apply the process of what we call the delayed column generation. We start with a limited number of patterns, which is far less than the total number of cutting patterns that we have here. And typically we pick the simplest patterns to start with, such as the first 3 here. We just cut the board into identical pieces for all the different types of boards that we need. And we formulate a restricted version of our problem, which will contain only the first 3 columns. So we are going to ignore the remaining columns for now, and we'll focus our attention on the first 3 columns by dropping the variables x4, 5, and 6. And in fact, in general, we don't even know, and we don't need to know how many patterns we can have overall. We just focus our attention on the restricted number of patterns, and then we will generate only the columns that can contribute to the optimal solution. So this way we can have significant savings in space requirements and solve our problem more efficiently. So let's write down the restricted version of this problem, which is what we call the restricted master problem. So we have this restricted master problem. It only has 3 variables, and we see that the corresponding matrix is diagonal, and the problem is really trivial to solve. So we just need to set x1 to 80 over 3, x2 to 50 over 2, and x3 to 100 over 2. Right, so and usually we are going to store the information about the optimal basis for our restricted master problem in the following form. So we'll store the matrix B inverse, then on top of it we will specify the optimal dual solution, and the optimal dual solution is given by CB transpose B inverse. Then we don't really need the z value, but we could put the value of the objective here, and then B inverse times B, the current basic optimal solution. In fact, it's part corresponding to the basic variables, right? So here we'll have the column for listing the basic variables, and we'll have the list of basic variables here. For our starting restricted master problem, all of this is trivially determined. So first of all, note that the vector of the coefficients for the variables in the objective is given by all ones. Then the matrix B inverse for this diagonal matrix is trivial to determine. So we have B inverse given by 1/3, 0, 0, then 0, 1/2, 0. And 0, 0, 1/2. So for CB transposed B inverse, we need to multiply the vector of all ones by the matrix B inverse, and we will obtain 1/3, 1/2, 1/2. Then for the objective value, we'll have 80 thirds plus 25 plus 50, which gives us 305 over 3. And B inverse times B, the values for the basic variables are given by 80 over 3, then 50 over 2, which is 25, and 100 over 2, which is 50. And our basic variables are x1, x2, and x3. Now, this optimal solution to the restricted master problem also gives us a feasible solution to our original LP with many more columns, right? But that solution may not necessarily be optimal for the original problem. If this solution is not optimal for the original problem, then there must be columns from the original problem that should enter the basis here. So we should have some variables that will enter the basis because their reduced cost is negative. So we need to find the variables with negative reduced costs that could enter the basis to improve the current solution to our problem. So how do we find if we have a variable that's a candidate to enter? So we need to compute the reduced cost, right? So which is given by Cn transposed minus Cb transposed B inverse times n. And we have the vector Cb transposed B inverse, which is the dual optimal solution given right here. So let's denote this vector by y. So then this becomes Cn transposed minus y transposed n. So this is y transposed, in fact. And then the Cn transposed vector is just the vector of all ones, right? So therefore we have 1 minus y transposed n. And we are trying to find a non-basic variable such that the corresponding entry in this vector of non-basic variable coefficients is negative. So if we stick to the Danzig rule of selecting the entering variable, then we really want to minimize 1 minus y transpose times nj, where j goes over all the non-basic variables, or more generally we could say that j goes over all n variables. We could include the basic variables in this mix as well. We know that for the basic variables the reduced cost is going to be equal to 0 anyway, and if a basic variable was to give the minimum here, this would mean that the minimum is 0, and the current solution that we have for the restricted master problem is in fact optimal for our initial problem. So we are trying to find the smallest reduced cost among all the variables, and if that smallest reduced cost is given by 0, then we conclude that we have the optimal solution for our original problem and we don't need to do anything else, right? But then if this reduced cost is in fact less than 0, then we will have an entering variable that we'll need to use in order to improve the current solution and update our restricted master problem with an additional column. So this process is what we call the column generation, and to generate our column we need to produce the optimal solution to this problem. So we call this problem the column generation subproblem. Or CGSP for short. So in our case we can see that this minimization problem can be equivalently stated as the problem of maximizing this part right here. So also observe that our columns are given by AJs, the cut patterns. Therefore we can formulate our problem as the problem of maximizing Y transposed AJ over all the possible cut patterns for j between 1 and n. So this is our column generating subproblem, right? And we could enumerate all the cut patterns and then pick the one that gives us the maximum product with the optimal dual variable vector. However, as we said, we don't really want to generate the list of all the cut patterns explicitly. Instead, we can treat these entries in the vector aj as variables and try to generate only the cut pattern that we need, that maximizes this expression here. So in our particular case, we have aj given by a4, a6, and a7, and then the objective of our column generating subproblem becomes to maximize y1 times a4 plus y2 times a6 and then plus y3 times a7. And of course a4, a6 and a7 are the variables here, so we are trying to determine the cut pattern that we want to add to the mix here. And in order for a4, a6 and a7 to constitute a cut pattern, we need to make sure that the total amount that we cut does not exceed the width of our board, which is 15, right? So the total amount that we cut is going to be given by 4 times a4 plus 6 times a6 plus 7 times a7, and this needs to be less than or equal to 15. And then of course we have a4, a6 and a7 are all non-negative and integer. So this is our column generating subproblem for our problem that we are looking at. And here y1, y2 and y3 would be the values of the dual variables that we get from here. And we can see that actually the problem that we have to solve as the column generating subproblem for the cutting stock problem is nothing else but the classical knapsack problem. So we can apply a dynamic programming algorithm to solve this problem to optimality. And then once we solve the column generating subproblem to optimality, there are a couple of possibilities here. If the optimal objective value for our column generating subproblem is less than or equal to 1, then our minimum here is going to be greater than or equal to 0, meaning that the optimal solution to the restricted master problem that we have is in fact optimal to the original problem. Then we would stop. There are no candidates for the entering variables, right? So we reach the optimum. The second possibility is when the optimal objective value for the column generating subproblem is actually greater than 1. Then in this case, what will happen with the minimum here? It will be negative, so the reduced cost for the column corresponding to the optimal solution of the knapsack problem here is going to be negative. Therefore, this column will enter the basis of our restricted master problem. We are going to generate a new column corresponding to x4 with the coefficients given by A4, A6, and A7. And as a result, we will obtain a new expanded version of the restricted master problem. And then we'll proceed to solve the restricted master problem and find the optimal solution. And then again, try to see if column generating subproblem yields optimality to the original problem or generates a new column, and we keep going generating the new columns until we reach the optimal solution to the restricted master problem that we can certify as optimal for the original problem. So returning to the data for our particular example, let's solve the corresponding column generating subproblem. We have y1 given by 1/3, y2 is 1/2, and y3 is 1/2. So our column generating subproblem is to maximize 1/3 times A4 plus 1/2 times A6 plus 1/2 times A7, subject to 4 times A4 plus 6 times A6 plus 7 times A7 is less than or equal to 15. Then A4, A6, A7 is greater than or equal to 0 and integer. So we have this knapsack problem, and we can solve it using the dynamic programming algorithm. Or alternatively, since we already have all the patterns listed in a table, we can just check which of the patterns has the highest objective. So we have the coefficients of 1/3, 1/2, and 1/2. And if we go to our patterns here, then we can see that both fourth and fifth pattern will yield the optimal objective value for our knapsack problem. So we'll have 2/3 plus 1/2 will be the optimal objective value. So let's go with the column 4 here. So our optimal solution is given by A4, which is 2, 0, and 1. And our optimal objective value, let's denote it by W, is given by 2/3 plus 1/2, which is 7/6. So clearly it is greater than 1, meaning that the corresponding reduced cost will be given by negative 1/6, which is less than 0. So this will be our entering column. Now we are going to update our optimal basis, and we'll compute the new B inverse and the corresponding dual solution given by CB transpose B inverse. So let me copy the data that we have here. First of all, we need to convert the entering column to the basis that corresponds to the basic variables x1, x2, and x3. For that, what we need to do is multiply B inverse by A4. So we obtain B inverse times A4 is 2/3, 0, and 1/2. And also our objective value for the column generating subproblem was 7/6, and our reduced cost was -1/6, right? So the entering column will look like this. So we have 1/6 in row 0, and then we have 2/3, 0, 1/2. So this is our entering column. And next we apply the ratio test. We look at the right hand side column and divide the entries in the right hand side column by the corresponding positive entries in the entering column. So for the first row we'll have 80/2 is 40. Then the second row doesn't participate in the ratio test because we have 0 here. And then we have 50 divided by 1/2 is 100. So the winner of the ratio test is this row right here. This will be our pivot element. So we proceed to update the table here by multiplying this row by 1/2/3, so which is 3/2, right? As a result, the new row 1 is gonna be 1/2, 0, 0, 40. And the basic variable corresponding to this row is going to be x4. So x1 is leaving the basis, x4 is entering the basis. And then we need to update the second row and the third row. For the second row, we already have 0 in this column here. Remember, we need to make all entries in this column other than the pivot element equal to 0 by applying elementary row operations. So we just copy the second row here, 0, 1/2, 0, 25, and the basic variable is still x2 here. And for the third row, what we need to do is multiply this by -1/2 and add it to the third row from here in order to obtain 0 in this position. So we multiply 1/2 by -1/2, add 0, we get -1/4. Then we have 0 for the second entry in this row and 1/2 for the third entry. So this is our new B inverse. And the right hand side here is going to be 50 minus 1/2 times 40. So we get 30. And the third basic variable is x3. And now we just need to specify the objective value and the values for the dual variables. We could do it also using the elementary row operations, but perhaps it's easier to do just by multiplying B inverse by CB transposed from the left. CB transpose is given by all ones, so essentially the dual variable values will be just sums over these columns here. So we'll have 1/4 for the first column, then 1/2 for the second, and 1/2 for the third. And the objective value is given by CB transposed B inverse times B small, which in our case is just the summation of these entries here. So we have 40 plus 25 plus 30, which gives us 95. And this completes the pivot operation. So we obtain the new values for the B inverse matrix. We obtain the new values for the dual variables, for the objective, and we can see that this basis is optimal for the new restricted master problem. And by the way, the new restricted master problem is obtained from the old one by adding the column for A4. The column for A4 was given by 201 in the constraints and of course by 1 in the objective. So if we were to specify the restricted master problem which we are solving right now, then here is how it's gonna look like. So we make some space for the new variable that we are adding, and the additional variable will be x4. So we add x4 to the objective, and we add the column corresponding to x4 in the constraint. So that was given by 201 times x4. So this is our new restricted master problem. Of course, non-negativity of x's is there, so we just keep it in mind and don't write it explicitly. And this provides the optimal basis for the restricted master problem. So we are now ready to formulate the column generating subproblem. We use the optimal values of the dual variables as the coefficients in the objective for our knapsack problem. So we have maximize 1/4 times a4 plus 1/2 times a6 plus 1/2 times a7 for the objective. And then of course we have the feasibility for the pattern given by 4 times a4 plus 6 times a6 plus 7 times a7 is less than or equal to 15. a4, a6, a7 are non-negative and integer. And we need to solve this knapsack problem in order to figure out if we can add any more columns to improve our current solution. So looking at the coefficients of 1/4, 1/2, and 1/2, and going back to our table with patterns, we see that if we use the coefficients 1/4, 1/2, and 1/2 for either column 5 or 6, which are the only remaining columns, we will obtain the objective of 1. So we have alternative optima for our knapsack problem, but in both cases our objective is equal to 1, and because of this the reduced cost is 0, so we don't have any more entering variable candidates. So we conclude that the solution that we found is optimal because there are no more entering variable candidates, and we are ready to report our optimal solution. We see that x3 is equal to 30, x2 is equal to 25, and x4 is 40. The total number of boards that we have to cut is 95, and this is our optimal solution given by z star equal to 95, and then x1 star is 0, x2 star is 25, x3 star is 30, and x4 star is 40. So we are using only 3 different cut patterns to produce our optimal solution.